this is the time response analysis of the C of t values for unit step response. Omega n is equal to 6 radians per second. So these are the graphs. I derived it with the help of software called MATLAB. This is the response of the system, and beta value is equal to 0. And this is the response of the system, and beta value is equal to 0.1. This is the response of the system, and beta is equal to 0.2. This is beta is equal to 0.3. This is for beta is equal to 0.4. This is for beta is equal to 0.5. This is beta is equal to 0.6. And this is beta is equal to 0.7. This is beta is equal to 0.8. This is beta is equal to 0.9. And finally, this is beta is equal to 1. If you observe, as the value of beta is increasing, then amplitude of the oscillations is decreasing. Okay, the amplitude of oscillations are going to be getting increased. So here, if beta is equal to 1, that response is called critically damped response. If beta is equal to 0, that response is called underdamped response. Undamped response. Response if beta value is equal to 0, the response is called undamped response. And if beta value is lying between beta value 0 and 1, then we call that response as underdamped response. So during underdamped response, what happens is the magnitude of the oscillations are getting decreased. Okay, so based upon this, here we define certain parameters over the time response analysis. This value is known as peak value, and this time, the time to reach the peak value is known as or is called as peak time, and the response is settling down at a value equal to 1 as t is tending to infinity. This is known as steady state value. And the time that is taken by the response to attain this steady state value is known as stability time. And the time taken by the response to attain 90% of its value 90% of its final value is known as rise time. It is represented with T R. And the difference between the steady state value and the peak value is known as overshoot or peak overshoot. It is represented with MP. So all these are called as the time domain specifications of a second order underdamped response. So let us see, or let us define the time domain specifications of a second order system. Time domain specifications of a second order system. First one is rise time. Second one is peak time. Third one is peak overshoot. The fourth one is settling time. And the fifth one is steady state error. So first we define rise time. Let us see how we define the rise time. Rise time of the system is defined as it is the time taken by the response to attain 90% of its final value. Or steady state value. It is the time taken by the response to attain 90% of the final value of steady state value. Now we try to understand what is meant by final value. Final value of response or steady state value of response is that value of P of T as T tends to infinity. So steady state value is represented with PSS. PSS is equal to limit as T is tending to infinity P of T. This value is known as steady state value of this. Here, coming to the rise time, The definition of lifespan, it is the time taken by the response to attain 90%. 90 by 100 into TSS equal to 0.9 TSS. So, the time taken by the response to attain this value is known as its lifespan. Okay, here, coming to this diagram. I am taking one particular response somewhere here 0.9 will be there. 1 is its final value. So this time is known as the rise time. The rise time is defined, represented with T suffix R. So the next parameter is peak time. The peak time is represented with T suffix P. Peak time is defined as it is the time taken by the response to attain its first peak. As I told you, the underdamped response will have different peak values that I will show with the help of the figure. Let us go to the figure now. Here, you take theta is equal to 0.1 value. This is the response for theta is equal to 0.1 value, right? It is having an oscillatory response. If you observe, the magnitude of the peak value is decreasing for every cycle. Isn't it? So, it is the maximum value during the first cycle, and this is the maximum value during second cycle, and this is the maximum value during third cycle. So, it is the time taken by the response to attain the peak value during the first time. So, this is the first time the response is attaining its peak value. So, it is the time taken by the response to attain this value is known as peak time. So, somewhere here, it would be there. So, this is the peak value. Peak. Next one is peak over 2. The peak overshoot is defined as the difference between the maximum value of the response to its final value. So, the response will attain its peak value to our maximum value when T is equal to T. So, T maximum is equal to C of T. The peak overshoot is represented with MP. So, peak overshoot MP is equal to P of EP minus P of infinity. In general, this peak overshoot is expressed as a percentage. So, percentage peak overshoot, percentage MP is equal to P of EP minus P of infinity divided by P of infinity into 100%. So, for zeta is equal to 0, this percentage peak overshoot is equal to 100%. Sorry, 200%. Because the C of infinity never be equals to 1. As zeta value increases from 0 to 1, this percentage peak overshoot decreases. And percentage peak overshoot is negative for an overdamped system. That means if the damping in the system is greater than 1, then there won't be any peak overshoot exist in the response. The next specification is settling time. The settling time is CTLE. The settling time is represented with TS. It is defined as it is the time taken by the response within plus or minus 5% or plus or minus 2% tolerance band of its final value. Say, what is meant by tolerance band? For low zeta values, The system response is oscillatory and it takes more time to settle down. So in such cases, if we observe the response characteristic, then this is the final value where the response is required to be settled down as t is tending to infinity. But the response will oscillate around the final value and finally it settles down. So this oscillation, if it lies between 1.05 and 95%, then this is called as 5% tolerance band. Suppose if beta value is little bit high, then automatically the system response will settle down like this. This is the band 1.02 and 0.98. This band is known as plus or minus 2% tolerance band. So, as the time is increasing from 0 to infinity, the response C of t should settle down around its final value. So, if it is settling down in the 5% tolerance band, it may settle down within the 2% tolerance band. Then, the time at which it settles down is known as settling time. The settling time for the response to attain 5% of its tolerance band value is 3 time constant. And to settle down within the tolerance of 2%, it takes 4 time constants to settle down. So, the units of the settling time is in seconds. As we know that the time constant unit is second. Okay, so the settling time for 5% tolerance band is t into 3 time constants. For 2% tolerance band, it is 4 time constants. Next is steady state error. Before going into the definition of error, steady state error, let us try to understand what is meant by error. The error is defined as the difference between the reference input to the output what we obtain. So, E of t is the error and bar of t is the reference signal and P of t is the output. Then the difference between the reference input and the actual output what we got is defined as the error. So here, error is the difference between the reference value and the response. Now, what is meant by steady state error? Steady state error is the error of the system the value of E of t as t tends to infinity. And the steady state error is represented with ESS. The value of ESS is equal to limit as t is tending to infinity E of t. If you have the Laplace transform, then this value is limit as s is tending to 0, s into g of s is known as the steady state error of the system. So these five parameters are very, very important, and we will derive an expression for all these five parameters.